Okay, so we're going to start where we always do, shape functions. So we're just going to use a linear interpolation here for a triangle that's 1, x, y. A is going to be x evaluated at 0, 0. So we're going to use a node numbering scheme that where the local node number starts in the lower left corner. So 1, 2, 1, 2, 3. Okay. So that's x All right, so nothing new there. You guys should be getting tired of seeing that. Right? That's nothing's changed. That's exactly the same shape functions we've developed before. Okay, but now we're going to create this shape function matrix, and I'm going to use a little trick to do it. I'm going to define a variable zeros. That's going to be a constant array of zeros. That's the length of NN. Alright, so in this case it's just 3 zeros. And then I'm going to use this Mathematica function called riffle. So I'm going to riffle NN with zeros. What do you think that's going to do? It's like shuffling a deck of cards, right? Perfect little riffle shuffle there, okay? So I'm going to riffle first NN with zeros and then zeros with NN. You can see what the difference is, right? So that produces N1 0, N1, N2 0, right? So if I just combine these into a matrix, we can look at it like a matrix. There's our shape function matrix, okay? That my Freudian slip always refers to. Now we actually have a matrix. Okay? So here, the next thing I'm going to do, I'm going to introduce you guys to some really quite advanced Mathematica programming, but very, very powerful. In the context of this problem, but as an aside here, I'm just going to show you. Like, we all know that we can take, say the derivative of x squared with respect to x. That's going to give us 2x. Okay. We can do something in Mathematica called functional programming, where we can use this. Don't worry about the particular syntax, but if I put #1 there and put an ampersand here, that turns this into a pure function, okay? And so I can call that anything. I'll call it f. That's just a pure function. Now I can call f like that. See what I did? So I essentially took what's on the right-hand side there and made this pure function, assign it to f, and then I can call f like that.
Is that like using the x underscore command as well, or is that found one significantly different from that?
It's different, okay? And so for just this simple case, it's not very obvious the power, okay? Another way you can use the syntax where you say, so here I define a pure function, and then if I say /at, this means map. So I'm going to map that pure function over the list that's going to contain x squared, and I get that. Okay? So I just did the same thing a couple of different ways. Don't worry about the exact syntax. This class isn't about you being mathematics experts, but I want to show you this exists. And then here's where the real power is, okay? So it's not that interesting when because there's no difference than if I just put x squared instead of hash 1, right? But here's where the real power is. I can map this over an entire list. So now let's say I have 2x, 7, x to the third, 20, 11, x to the fifth. Now, you see what happened? I mapped that pure function over that list such that it took the derivative of each of those terms in the list. Okay? So I'm going to use this. This is called functional programming. I'm going to use this in the next step, right? Because if you remember, that D matrix is a matrix of differential operators, right? Partial, partial x, partial, partial y, right? And I want to multiply D times something, and then I want it to actually perform those evaluations. So I'll try to give you a counterexample to what I'm saying. But so what I want to do, I'm going to create that D mat, okay? What that is all right, so in that syntax, it may be a little bit clear, partial, partial x, 0, 0, partial, partial y, partial, partial y, partial, partial x, okay? So if I just simply say dmat times nmat, I get nonsense. Okay, what I really want to do is I want to perform, I want to say partial, partial x of this, right? I want it to perform that evaluation. Okay, so the way I'm going to do that is with something called inner. So inner is a generalization of dot product, if you will. And I'm going to use some more functional programming again. Don't worry exactly if you don't understand this stuff, but I just want to show you, kind of the outcome can be pretty cool. We're going to create this is another pure function right here. So what this is essentially going to do is map, it's going to place dmat where that number 1 is, and then nmat is going to go where number 2 is and will be replaced in that number 1 here in the dmat, and then it's going to map over the entire matrix. It's going to perform all the operations, and I'm going to get the answer I want, just as if I would have worked it out by hand, right? And this is easy enough. We could have worked it out by hand. I could have just wrote down the answer. It's just a 2 by 3, so it's not that big a deal. But if it was 100 by 100, it might be a bigger deal, and you can use Mathematica to help you do it. So there. That's the B matrix. All right. So again, I don't expect any of you, very few of you, if any of you, really completely understood what I just did. But essentially, I just used these functional programming style to perform a calculation that I could have done, that only otherwise could have done by hand. There's no equivalent way to do this in MATLAB, by the way. This can only be done in MATLAB. Even using MATLAB's symbolic package that I know of, there's not a way to do this. It's certainly not this slick way in a functional way. You could probably do it in a loop, which would not be near as efficient as this. Okay, so now we have B. We're going to go to our C matrix, okay? Now we're going to use, before we just had C1, C2, C1, 1, C1, 2, right? And then depending on if we were in plane stress or plane strain, determine what those values of those took on, right? So we're going to assume this is plane stress. And so if you just look back in your notes, the conditions for plane stress have these properties. All right, so I just plugged and chugged from the notes there. And now we're essentially ready to find what KE is. So we can say we're going to perform that integration from 0 to A in the x direction, and then from 0 to what? In the y direction. That line. The line that goes from 1 to 3, right? So then we just have HE, B, transpose, C mat, B, Y, X. So that's the stiffness matrix for plane stress condition for a triangular element. So the only thing we'd have to do for a rectangular element is change the shape functions, change the limits of integration. We got it, no problem. Okay?